Imagine taking a difficult class, but every 5 seconds your memory is wiped clean. You hear a word, write it down, and then poof, it vanishes. This diagram shows how early artificial intelligence processed information. Data moves in one strict direction, from the input layer, through the hidden layers, to the output. It looks at a single piece of data, decides, and then deletes it. That approach works well if you want a computer to recognize a single static picture, but it creates a problem for human language. Words don't exist in isolation, and sentences don't have a standard fixed length. To understand the end of a sentence, you have to remember the beginning. To solve this, computer scientists developed the Recurrent Neural Network, or RNN. Instead of pushing data in a single straight line, an RNN has a loop built right into its architecture. It takes what it just learned and feeds that context straight back into its next step. By carrying the past directly into the present, the network maintains an ongoing record. It stops resetting with every new word and begins acting as the ultimate note-taker. This timeline illustrates how that loop looks when we stretch it out. If the network reads the phrase, "the happy cat sat," it processes the sequence one word at a time. As it moves forward, each step hands its current notes to the next box in line. This mathematical formula is the actual recipe the AI uses to write those notes. It looks complex, but it is built from a few highly logical pieces. The symbol XT represents the present. That is the brand new word the network is looking at right now. The symbol HT-1 represents the past. That is the running notebook passed down from all the earlier words in the sentence. Next to those, we have the letters W and U. You can think of these as balancing scales. They tell the network exactly how much weight to give the brand new word compared to the old notes it has already taken. Finally, all of that balanced information passes through the letter F. This acts as a filter. It squishes the data down so the system doesn't get overwhelmed and spits out HT, your newly updated note, ready for the next word. This repeating calculation empowers the computer to track context step by step. It takes a string of isolated words and connects them into a single, mathematically grounded sequence of meaning. But if you sat in a 3-hour lecture without ever starting a new page, your notes would eventually become useless. If a sentence goes on for too long, the standard RNN runs into a similar roadblock, where its running notebook gets completely cluttered. Computer scientists call this the vanishing gradient problem. As a sequence gets longer, the network's earliest memories get watered down. By the time it reaches the end of a long paragraph, it has forgotten how that paragraph started. To solve this, researchers built an upgrade, the Long Short-Term Memory Network, or LSTM. It uses the same looping structure, but it has a much more selective notebook. This internal mechanism uses things called gates. You can think of these like a student holding an eraser and a highlighter. The eraser deletes useless filler words, while the highlighter grabs crucial subjects and verbs, locking them away in a protected memory vault to be used much later. LSTMs overcome the memory limits of early networks by actively filtering their data. They calculate exactly which words to keep in their memory and which ones to discard. You rely on this looping memory every day. When you type a text message, an RNN is reading the words you've typed so far, consulting its running notes, and using that context to guess the next logical word. This happens in sentiment analysis too. If you feed an RNN a movie review, it reads the entire paragraph line by line, updating its notes with every word. Only after it reaches the final piece of punctuation does it use its complete summary to decide if the review is positive or negative. These tools work because the AI waits, reads the full sequence, and consults its compiled record before making a decision. Translation software uses a specific version of this architecture, called an encoder-decoder model. One RNN reads a sentence in French to build a master set of notes. Then it hands those notes over to a second RNN, which uses them to write out the same meaning in English. Whether it is translating languages or predicting your text messages, the underlying principle is the same. Human language is a sequence of moments unfolding over time. By giving AI the architectural ability to loop the past straight into the present, researchers moved beyond fixed-size processing and allowed computers to handle the continuous, unbroken flow of human communication.